All right, so in this video, we want to go over partial fraction expansion. And partial fraction expansion is used when we're trying to find the inverse Laplace transform of a function that we can't use directly with a table. We have to kind of manipulate it and put it in a different form, and then we can use a table to find the inverse Laplace transform. So notice one good way to see if you're going to need to employ a partial fraction expansion is to compare your problem to one of the forms in the table. So if we notice here, we're given the problem, find the inverse Laplace transform of 2s over s minus 2 times s minus 3 times s minus 6. We don't have basically any form that matches this, and there's nothing we can do. We had seen before that we could probably try to factor stuff out and put it in a particular form, but in this case we can't really do anything with this problem with the tables as it stands. So this is where we're going to do something called partial fraction expansion. We're going to basically set this whole equation or term here, right, equal to these smaller individual terms here. And a key to seeing what we're doing here is we're doing A here, B here, and C here. These are constants, and we're going to want to determine those. But they're constants. They're real constants. They're like, it could be 5 or 20 or something like that, or 1 over 5 or something like that. And we're going to want to determine those values. These on the bottom are the terms, each individual term from the original problem that we have. You notice we have s minus 2, s minus 3, and s minus 6, just like here. So we're going to start there, right? We're going to set our whole problem equal to some constant over one factor, some constant over another factor, and some constant over another factor, which we'll have to find. So step 2 is, since we have this equality sign, right, we can multiply this s minus 2 times s minus 3 times s minus 6 to all the terms. And after a couple of cancellations, right, you see s minus 2 here, and s minus 2 cancels, s minus 3 and s minus 3, and s minus 6 and s minus 6. We end up with this long equation, right, 2s equals this term plus this term plus this term. All right. So in step 3, basically we want to find A, B, and C, right? That's the whole goal of partial fraction expansion. And the way we do that, one of the quickest ways to do that, is to try to see if we can cancel out some terms so that we can isolate like a single unknown. What I mean by that is, imagine it, for example, if we set s equal to 3. If we set s equal to 3, then we can plug in 3 everywhere we see an s, and we can actually solve for b, because in this term 3 minus 3 is going to be 0, 3 minus 3 is going to be 0 here, and we have just 6 equals b times 1 times negative 2, and we can simply solve for b, and b is negative 2. And in a similar fashion, for step 4, we say, okay, we already know b. We could plug b here for negative, b equals negative 2, and that might be a good practice to do. In this problem, it'll work out where we actually don't have to use b to solve the problem, because if you notice, let's say if we let s equal to 6, right, then we're going to cancel a and b here. We get to solve for c individually, right? We don't have to worry about what b is. It doesn't matter what b is because this whole term is going to be 0 anyway. So that's what we mean there. So c ends up being 1. And then similarly in step 5, if we let s equal to 2, then this whole term cancels. 2 minus 2 doesn't matter what b is. 2 minus 2 is 0. Doesn't matter what c is. We could plug it in or not. The whole term, this whole part here is going to be 0. And we're going to end up with a being 1. So remember we had written our formula as a over s minus 2 plus b over s minus 3 plus c over s minus 6. But we found a, b, and c already, so we can actually rewrite them using the numbers here. So let's see, right here, 1 over s minus 2 over s minus 3 plus 1 over s minus 6. We have this minus here because it was a negative 2. B was equal to negative 2, so we just put, instead of plus negative, we just put minus here. It's the same thing. And so what we've done is we've successfully rewritten this complicated looking term here with a lot of factors on the denominator as a simpler form. But what we've done is we actually can use the table of inverse Laplace transforms to solve this problem here. We have the inverse in step 7, if we look here, the inverse Laplace of this entire portion here, these entire terms, is equal to the individual inverse Laplace transforms, all just added and summed together, subtracted also because we have a negative here. So we have an inverse Laplace of 1 over s minus 2, minus 2 times the inverse Laplace of 1 over s minus 3. That's coming from 2 over s minus 3, where we pull the 2 in the front, right? Because it's a constant. And then that's plus Laplace of inverse Laplace of 1 over 6 minus s minus 6. And we end up using one of the forms in the inverse Laplace transforms where we end up with e raised to the 2t minus 2e raised to the 3t plus e raised to the 6t. And this is the 1 over s minus a is equal to e raised to the at.